We've got a pretty good quorum, and even though the clocks outside are a little behind, we'll go ahead and get started since it's still second to the last session of the day. So this is the Optimizing Performance in LabVIEW RT Advanced session. My name is Deborah Burke. I'm the product manager for NIWeek's Realtime as well as the LabVIEW Realtime module. I'm stationed here in Austin.
Mike Altmann, I'm in LabVIEW R&D. I'm a software quality engineer for LabVIEW.
Okay, so this session, we're going to go through the different stages of designing a real-time system, all the way from the design stage to the actual development stage to the deployment stage. And we're going to go through some recommendations on optimizing performance for those systems and some of the settings that are recommended to get the best use out of those applications. Question? That's Mike. Is that any better?
Yeah.
Okay, great. Okay, so I'm going to kick it off on the design side. So we'll talk through a couple things. First is just creating a design diagram. Common sense, but just want to make sure to state it because sometimes folks just dive into programming a specific piece of it and aren't thinking about the big picture or maybe what are some future requirements that might get introduced, by your end customer that you kind of didn't plan ahead for, and then how to create those. So first, rhetorical question, but why is it important to create a design diagram? Why do you need to think about your architecture before you get started? It's especially important on real-time systems because you have a limited set of resources. So you need to think about what are my critical tasks up front and make sure down the line you aren't trying to add and bolt on more and more and more because you need it to be a reliable system. So there's many types of diagrams you can do. You can whiteboard it, you might be building it out in PowerPoint, Visio, state diagram. But just a key recommendation is to think about the entire system, including what maybe your NI real-time system needs to communicate to upfront. One of the tools we use internally in lieu of Visio is a tool called YED by YWorks to create design diagrams that we use to put tasks on certain controllers or targets. For example here, real-time FPGA and Windows. And it's nice to also be able to highlight what types of data communication is happening in the system. So here, every yellow box is indicating a loop. And then also a critical piece to think about on the onset is what are my requirements for data communication? Are there certain protocols I'm limited to because I need them to be secure? Or am I doing a streaming type of application that I need to be sure it can be a buffered data communication transport, for example? So when you're thinking about kind of making this diagram, one of the key parts I want to call out is the data communication element. So when talking about data communication, we try to separate into three paradigms. Instead of just jumping to an API, how do I need to transfer this data, and where is it going between? So the first type of data communication is tag data. This is a single point, latest update value, and often is lossy. So this might be something just like checking the temperature. I need to check this tag every once in a while, and I really just need to know if the value changed or not. The next one, which has a little bit more to it, is messaging. So this is intermediate. You often want this to be low latency, like I need to issue this command, and there might be some acknowledgement that you need to build into that to ensure that that message arrived. And then lastly is streaming. So this is likely some sort of waveform data, something coming through at a high rate that you need high throughput on that. You might need buffering on one or both ends to ensure that that's transferred losslessly. And you might even put some checking of the underflow and overflow to be sure that you're not filling up those buffers. So when you're doing data communication, think in terms of these paradigms. And then from there, when you're creating your design diagram, you can start to get down to the API level. So when you're walking through this, just an example application, I build my design diagram, then maybe I'm going to start coding the FPGA first, or then move to real-time, for example. So this is taking from one of the real-time control sample projects here. You can see that the application went from the design diagram to modular sub-VIs for each of those tasks. So I have one for watchdog functionality. One here is based on the queued message handler and is my main message handler group. So this is going from design diagram to coding. Thinking about your initialization routine up front there as well in your design. So you might have certain I/O you want to put at a default starting state, or you might have some startup scripts you want to run, for example. Then you can implement your data communication. And then finally, creating a safe shutdown routine is another recommendation in the planning cycle. Okay, for having reliable architectures to start to design from, within the product we have our sample projects for both real-time and FPGA-based products, both for Compact Trio and for DAC. So these can be something that you learn best practices from and how to implement a modular architecture, or you can even start from them as a way to architect your design, and then you just place in what I/O you need to and your application IP algorithms, etc. Another new architecture that is built via our SE team, our Embedded Systems Engineer team, is called DCAP, or Distributed Control and Automation Framework. This is something that's built off of the SCAN engine for Compact Trio, and is a robust application they've used in tens of embedded systems now that they've designed for end customers. So this is something new that we're looking to promote this year and get the word out. There's another robust starting point. It's open source. You can go in and create your own plugin modules for this. But it does a lot of the standard I/O management as well as configuration and optimization that are built in. So there is a booth down at the expo floor, or if you're interested, I've got a business card here. I can get you in touch to learn more about the DCAP framework. There's also a hands-on session, which I'll mention at the end. Okay, now for the development section, I'll hand off to Mike.
You guys hear me all right? In the back, hear me all right? All right, great. All right, so we're going to get into talking about kind of development. So you've kind of planned out your application. Now you want to get into developing it. So let's talk about a couple things about real-time. So what is real-time? So real-time is the actual time during which something happens. Right? What's real-time computing? Okay, so that's when you have a hardware or software system that guarantees a response to some kind of event in a specified amount of time. So we have real-time, we're computing in a specific amount of time, and now we have real-time operating system. So what does a real-time operating system do? It allows us to operate on a certain hardware platform and actually execute these tasks in a specified amount of time, so we know we'll get a response, or this algorithm will run in this specific amount of time. So when we're thinking about that, a lot of our functions can run various times depending on what's going on our operating system, other tasks that may be happening. So when we look at that, we have something that we call jitter. And so that's the range in time at which it could take a specific algorithm or whatever it is to execute on your target. In this case, we're running between 1 and 2.8 milliseconds to do some type of calculation. Now, if what we really care about is that worst case execution time, is what's the longest period of time that it's ever going to take for me to get a result from this algorithm, right? And so here we have worst case execution time. If we set a bound above that, say we set that at 3 milliseconds, we know that we're guaranteed from our testing that it'll always happen in under 3 milliseconds. So I can say yes, in 3 milliseconds I can guarantee a response to whatever event happened. So taking this another level, now we have individual algorithms. Let's dig a little deeper and think about how this is actually going and being scheduled and worked on with our CPU. So we have threads, which are just concurrently running tasks. So those are things that are getting spooled up on your CPU. As far as thread priority, that's the rank of these things that are happening. So something might have a higher priority, needs to happen before some other task. And then we have execution systems. So these are just groups of threads that we use in LabVIEW to try to organize how we spool all these different things up. Another thing that comes in hand with threads is a scheduler. The scheduler is the thing that's assigning your different threads to your CPU and getting them executed whenever they need to be actually ran. And then we have a run queue, which is the things that are actually running currently on your CPU. So if we kind of pull all that together, you can look at NI's 3 real-time operating systems. So we have FarLap and VxWorks, and then we have our newer one, Linux Real-Time. So if we're looking at these, FarLap and VxWorks have a single scheduler. So basically that scheduler is responsible for scheduling both high priority tasks and our lower priority tasks or subroutines or anything along those lines. And so how this scheduler works is for our highest priority tasks, it uses a preemptive scheduler. So something that's a higher priority will preempt something else. For anything that's a lower priority, we schedule them at the same level, so then we get a round robin where we'll just grab whatever task is up and we'll schedule it. Now if we look at Linux, it's a little bit different. We actually have multiple schedulers on a Linux target. So we have a preempt RT scheduler, which works very similar as the other one, where our high priority tasks, things that we actually need to run in real time, get done in that specified amount of time, are going to run on that scheduler. We're going to run them through there, and they'll get scheduled on the CPU as they need to be. And then we have a completely fair scheduler for every other task that's running on Linux. So it's a little bit different how the Linux OS works compared to our other FarLab and VxWorks operating systems. So now let's take a little deeper dive into how LabVIEW itself actually is scheduling out your threads. So as you can see here, we kind of have a priority versus execution system graph. And as we go up in priority, we have certain limitations on what we can actually do in terms of scheduling. So if we look at the main application, this is your RTEXE as you deploy it to your target. By default, it has one thread in that main application execution system. Now, we have other execution systems available to us, such as the standard, and so on and so forth, and then we also have system threads. So this is where we're running system tasks, and we're also running NI code or processes that we might be running in the background. One example of that is one of our highest priority things, which is the NI scan engine. So it's the timer that's actually keeping your scan engine and getting those measurements when you need them. So now if you're looking at your other execution systems, we can fill this out. So we actually have a lot of different execution systems, and each of those has specific thread pools that they can actually use. So in the case here, we have above time critical here, which is our scan engine. Nothing can be higher than that. For user code, then we can set time critical, and time critical is a VI setting. So inside your VI, you can say, okay, I want this to be a standard or normal priority or time critical. And so time critical is going to schedule it up here. Now, if you're working in an execution system and say you assign that VI to the standard execution system, you can actually only have one thread per CPU from the standard execution system. So if you have a single CPU system and you have two while loops that are running in parallel in your VI that you sent to a critical time loop, you're actually going to be running both of those in serial. You're not going to be able to run those two threads in parallel. Now, you have a couple other options. One, which is to then assign those to different VIs and assign each VI to a different execution system, so you can have each would have their own time critical thread. Or you could bump down your priority if you wanted to schedule them. Or on systems where you have more than one CPU, you get another set of these. So you can actually have two threads, one for each CPU on your target. And that's where it kind of takes you more into the PXI systems where you have multi-core targets and those types of things. So now, if you kind of recall going back to what Deb was talking about, we laid out this diagram of how our VI is actually going to be shaped. What are different tasks we're going to have in it. So we have a control loop, potentially, a networking loop, and a logging loop. These are three tasks that we want to do in our RT application. Now, thinking about how we schedule, how our schedulers work, and how we want to, split up our threads throughout execution systems, we need to think a little bit more about what are our timing requirements for these different scenarios. So say our control loop, we know we absolutely need to get a response within 1 millisecond. So our algorithm has to run in that time period. That's guaranteed. Networking, maybe we want a 10 millisecond turnaround time. And maybe with logging, we want a 30 millisecond turnaround. So that loop will run every 30 milliseconds and we'll get whatever information we needed in there. Now this kind of brings us into this concept called the timing budget. So we have a maximum amount of CPU we can use, right? We can only use 100% of our CPU, we can't go over that. So when we're scheduling this out, we need to think of, okay, I have all these different loops running, and in this case, I have a control loop where I'm running my period of 1 millisecond, and my monitoring group with 10 milliseconds, and my logging group of 30 milliseconds. Now, that duration is the time it actually takes for that code to run. So through benchmarking and testing, I know that even though I want a result in every millisecond, I actually can run my algorithm faster than that. But if you look at the equation here, what we do is we divide the duration, the time it actually takes, divided by the period, so the time we really want it to take, and that gives us a percentage. right? And that's the percentage of the CPU that that single operation is using. So if we look at it closer here, we can see, okay, so that's taking up about 40%, and this is taking up, another set. And by the time we add it all up, we actually are using 123% of our CPU. So this isn't going to work out. If we deploy this application, we'd realize this right away that we actually, one of these, depending on which is the lowest priority, is not actually going to get ran because we're too busy running higher priority things. So this is kind of two concepts to keep in mind here. One, in the situation here, you want to make sure that your control loop, which is your highest priority, you need to get that control response out, needs to be ranked, at a higher priority when you're programming. Then you're like, okay, monitoring is probably my next highest, and then logging, if I can get around to it, I will. In this case, you're probably not going to. So our options are, well, one is to try to optimize our code and make the duration lower, and the other is to relax our constraints on the timing we want. So in this case, we're going to bump up our monitoring loop to every 25 milliseconds, and we're going to log every 80. So not that big of a change necessarily, but what it does is bring our CPU usage down to 72%. So as you're planning out your application and thinking about what you're doing, you want to keep in mind, okay, I also need to make sure all this can actually run and meet the timer requirements I have. Oh, you got a question? Sure.
So what do you recommend for CPU usage?
Definitely. So I have a slide on it later. I believe the recommendation is 72%. But we'll get to that in a second. I have a slide on it. Yeah?
Do you have to do any computations for context switching between threads on that, or is that taken into account here?
So typically that will be taken into account when you're doing your benchmarking. That'll be the next section we're talking about is getting into that. And I saw another hand potentially. Oh, sure. Repeating the last question was, do you have to account for context switching? So, OS overhead and switching from one task to the other when you're coming with this timing budget. And I said that typically it's included in your duration measurement, the context switching that would need to occur. Any other questions? Sure.
How did you do your duration measurement?
I will show you. So we have a couple different ways to do benchmarking with real-time. So I'll get into these different topics. So the first one is just a really simple benchmark. Basically, you place whatever code you want to run in a for loop, specify some number of iterations, and then get the time before and the time after and divide it. And it says, okay, so I ran it 100 times, I did this calculation 100 times, it took me 100 milliseconds, my average is 1. So that's a really simple way to do it. We also have benchmarking examples included in LabVIEW. So this is just an example. You can go to Options and Example Finder, and you can pull this up in real time under the real-time module examples. And in here, there's a lot more going on. Actually, what we do is you put in, whoops, wrong button. So you put in your initialization code here. So that's if you're allocating any memory or doing anything along those lines, you want to get that done before you actually get into executing your code, because those are types of things that can actually cause jitter in your code running. So you get your time, you get an initialization, and then you place your code here. We're going to run it the same way, multiple iterations, take timing measurements, and then we actually have a nice VI here that cleans it up and gives you a graph and a bunch of outputs of the timing, how long it took, what's your standard deviation, average time, those types of metrics around that. And that's where you can get that duration. Taking a step further, we also have another tool that's available, which is the Real-Time Trace Viewer. So this comes with the Real-Time module. It's a standalone executable, but what you can do is you can place VIs in your real-time application, a start VI, and that starts logging what's happening, and it's actually going to go in and it's going to log which VIs you have running, and it's going to show you which ones operating, which ones are waiting, and then it actually goes up here and it gives you even more detail in what thread is actually running and using CPU resources. And you can see here, okay, I have a standard time critical loop that's running, then it takes a break because I'm running something that's a different priority, and then I'll come back to run that. And then you can also see these flags. So there's a couple different things you can flag with the real-time trace viewer as well. You can flag memory allocations, you can flag mutexes, you can flag times where you're waiting on an object that's a shared resource. So say a lower priority loop is using some shared resource and your higher priority loop needs that, well, the lower priority code is going to have to finish before you can actually get there. So you can see all that type of different behavior actually happening on your real-time system, and then you can dig into it and see, okay, maybe I have to re-architect my code or change the behavior a little bit to get the timing I expect.
From the design standpoint, how do you implement, I mean, how do you kind of account for timing in a more complex application, one that may encompass thousands of VIs?
So that's definitely a good question. I think it would be doing modular benchmarking. So if you can break your VI into different types of tasks and get an idea of how much that time will actually take. So this is my monitoring section, you know, and this is my network communication section, and this is, you know, Modbus or something along those lines. You know, break it into your modules that you have and, you know, where they communicate with each other. Try to use that as drawing your boundaries. You know, if you kind of think back to like the design diagram we drew, we had kind of there's different communication paths between the different pieces of the program, and try to break it into bigger boundaries. Yep.
And you also show the application.
I'm sorry, can you say it a little louder?
Sorry. You had a website running on the
Mm-hmm.
and you always control the CPU usage of that one.
So if you have a web server,
Yeah.
can you monitor the CPU usage of your web server or control the amount it can use?
Yeah, it's more like the performance of once you perform like 2 kernels for the web server.
That's a great question. I might defer that one to the back of the room. As far as using, so the question was, if you're running a web server with your RT application, can you control what CPU and what kind of assignments your web server has separate from your real-time application?
You can use CPU pools. There's SMPDIs in the RT palette, and you can assign the system threads to a CPU and your time critical stuff to the other CPU, or like combinations of.
Yeah. Okay, so if you didn't hear him, we have a library of VIs, or the SMU VIs, which allow multi-core assignment, and so you use those libraries to assign specific sets of processors to, sorry, processor affinity is the term. Good question. Any other questions? All right.
Question
Oh,
on
geez.
Can we do that with DMA as well? You can't change the DMA CPU, DMA from an FPGA.
For FPGA, yeah.
To R2. You can't change that.
In terms of CPU, it would be assigned with the VI that's executing it. That bit of code, I believe. Any other questions? All right. So now we're talking about CPU usage. So we have all these resources, they're finite resources. So the first one that we're going to talk about is our CPU. So as we talked about before, what is a recommendation of how much CPU we should use? Ideally, we say around 70%. So this allows for any other cases that might be happening. If there's heightened network traffic and the network adapter needs to process more things, you have some extra CPU bandwidth available for those types of things to be processed. So ways that we can actually, you know, manage how much CPU we're using. One of those is a timing budget, so we can create that timing budget. We can make sure we prioritize code that we actually need to run in real time to be a higher priority. We can avoid excessive parallelism, so there is a cost to context switching. So, you know, switching between threads and scheduling those for the CPU and going back, that's going to cost time. So if you can potentially use a similar design pattern or benchmark your code, you know, run some things more serially, then you're not switching back and forth and using some overhead for scheduling. Offloading tasks. So their RT CPU isn't the only thing that you have available as a resource. You also have FPGAs. So You might need to push some of your data processing down to your FPGA, do some of it there, and then bring that up to RT. The other thing is streaming your data off of your real-time controller over to a server. So move that data off and let then the server do post-processing later, something along those lines. You can also use a host PC to help do monitoring and health monitoring of your real-time system as well. And then last but not least, sometimes an application just requires more power, some more horsepower. So you also might have the opportunity to upgrade to a Serio or PXI controller that might just have more cores and more memory available to it. Question?
So in the contract real environment,
Yep.
you have to account for, sometimes there could be some hot questions. Will it be during the call frequency as the compact radio and so on? Radio and so on. CPU usage, is that something that we should account for?
Potentially. That's more of a hardware question. I can't give you definite details, but yeah, I would assume that if you're doing benchmarking and you really want to get a benchmark of what it's going to be like and it's in the environment you're going to deploy it in, you should test it in that type of scenario. Any other questions? All right, so talking a little bit more now about memory. So memory allocations can impact the following things. So on a Serio can impact your reliability, well, any real-time system, your determinism. So when you're making a memory allocation, it's not a real-time task. It's not something that necessarily is deterministic. So it will take time for the CPU to go find, okay, I need a memory pool of this size. Do I need to move something around or whatever? Okay, here's my block of memory. Now you can use it. There's no guarantee on how long that time is going to take. So it can it can induce jitter into your program. And then it can also affect your performance. So memory allocations require CPU time. So your CPU is going to have to go off and do something else instead of executing on your code. So what are some things we can do to try to save memory or reduce our allocations? So pre-allocate memory whenever the size of memory that you need is known. So if you're generating some type of data in a for loop and you're going to run your for loop 100 iterations, beforehand generate an array, build that array, create an array, pass it in, place those elements in line, and then get your array out instead of just using the build array function inside of the for loop where every time we call it, we're going to have to get a larger and larger chunk of memory until we create that. Other things we can do is, if we're using queues or FIFOs, use fixed sizes. So in a queue, you can have it dynamically just ask for more and more memory, or you can say this queue is going to be a fixed number of elements, and it'll pre-allocate that memory, and then you can just use within the bounds what you allocated. Other option is to use RT FIFOs, where you're going to pre-allocate all of the memory space ahead of time, and then pass it around inside of that space.
Quick comment on the queues. Even if they're fixed size, they do not pre-allocate the memory space for that size of the queue. You have to actually get that number of elements inside the queue to allocate that memory. The RT FIFOs, they pre-allocate, but the actual queues do not.
Okay. All right, so avoid large string manipulation. So when you're, if you're adding strings or manipulating them around, every time we do this, we're going to have to make a dynamic memory allocation to put the new string in that space. And always close your references before shutting down your application. So if you're running like a real-time application and you didn't close your references, they may still be used in memory if you bring it back online without like a hard restart. We have a tool in LabVIEW that shows you buffer allocations. So you can enable this, and then as you look at your VI and your block diagram, you can see the areas where you're actually going to be allocating memory. So this is a helpful tool to see where in your application you might be doing that. And then last, there's a great guide called the LabVIEW Serialist Developer's Guide. And this talks about a lot of the information that we covered here, giving you more detail even than what we've kind of gone in here of best practices on how to make sure you're not overusing your CPU or your memory. So now we talked about kind of ideal states of where to set it. Now how do you actually figure out how much CPU usage or memory usage you're using? One of the tools that you can use is Distributed System Manager. So this is a tool that ships with LabVIEW. It's a standalone application. You can install a library, which is System State Publisher, on your Creo or your PXI controller, and that actually presents the information and publishes it, where then you can find your Creo and Distributed System Manager and then look at it and see, okay, how much memory usage do I have going on? What's my CPU usage looking like? Another option we have is the system configuration palette. So with system configuration, it's a set of LabVIEW APIs. Basically, you can connect up to your target and look at your system resources to get an idea of what your CPU load is or what your memory usage is, so you can actually see some of the same things that you see in Distributed System Manager, but you can do this programmatically. And you can run this either like on a host computer, or you can run it locally and get the information locally. So if you want your Creo to monitor its own memory and CPU usage, you can do that as well. And one thing to remember is that you kind of want you to spend your time that you're optimizing your code for memory and CPU usage, you want to make sure that's relative to the time you expect your controller to be up. So if you're running a 24/7, always up type of application, you're going to want to put a lot of effort and time into making sure you're not overusing your CPU and you're not leaking memory or making a lot of memory allocations along those lines, because those are things that over time can add up, and you start to run out of your resources. Whereas if you're running it, if you're developing an application, I'm only going to run it for an hour at a time on a test bench, and then I'm going to reset it. It's not quite as much worth your investment in making this the best RT code or optimizing it completely. So kind of keep that in mind as well. Question?
Sometimes we're using the distributed system manager in a dual core kind of CPU. I noticed that one of the cores has a very high performance and the other one is slow, and then it kind of switches back and forth. Is that a problem where like one of the cores is almost at 80%, 85%, the other one is at 10%, and then it's switching? Is it something internally the OS is balancing, or is that a problem?
So I'll repeat the question for everyone. So the question was, occasionally looking at a multi-core system, you'll see a particular core have a higher CPU usage and the other core having a lower, and then potentially that alternating in and out from one to the other. It's just an artifact of scheduling. It's the total system usage is the main concern that we're talking about here.
Okay. The other question I had was on the profiling tool that you showed there. The profiler also has a way to capture the sub-VI execution time. And initially you showed the benchmarking tool or something. Is there a difference between the two?
So looking at, are you talking about the real-time trace viewer?
When you go to tools, profiler.
Oh, VI profiling. Is there a difference between VI profiler and doing the timing in your code? Was that the question?
Correct.
So generally speaking, I think they use two different clocks. So the VI profiler uses a lower accuracy clock for timing, and when you're doing benchmarking, you're using a higher resolution timing source, so you can actually get a higher frequency, a more exact timing benchmark. So that's the main difference there. So you can, and potentially, you'll see variations in the time your code's running on RT where you can be pushing the limits of VI profiler.
What is the clock?
I don't know exactly off the top of my head, but for benchmarking, you want to use it's not the tick count, it's the real-time
Trace execution?
No. I forget the name of the clock, but it produces a double instead of a tick count integer.
It's called high resolution.
High resolution real-time clock. Thank you.
I just wanted to hit upon what he was saying before. So if you use a time loop, you can specify what core you want to use.
Mm-hmm.
And if you're not sure how many, like if you think you're going to use multiple different chassis CPUs or something, and you're not sure how many cores you're going to have at a given time, you can poll for how many cores the system
Mhm.
You just have to be careful not to set it to a higher number than the amount of cores you have.
Sure. I'm just going to repeat that for a second to make sure everybody heard it. Yeah. So he's mentioned when using a time loop, you can assign a time loop or time structure to a specific CPU. So depending on what type of target you're deploying it to, make sure you're aware of which CPU is being first available and which ones you're assigning to make sure you're not assigning everything to a single CPU and not utilizing other resources. One question here?
I was going to say, if you've got your time loop reasonably tight, you're not trying to do processing that should be done at lower priority inside your time loop.
Mm-hmm.
I don't think it makes sense to assign any more than a single core, because your RT system should be fast enough to do data, to do the kind of processing you need to do inside a time loop, which should be, I just finished my 50-point sample or 1,000-point sample. I have to put it in a queue and send it off to a lower priority, or put it in an RT cycle. That takes almost no time. If you've got a core dedicated to it, when that event fires, it will run. And it will be really deterministic.
Thank you. One more question in the back?
Do you want to assign cores on a time loop, or do you want to let LabVIEW handle that? Is it smart enough to kind of figure out where the best place for that to go?
So it's really your preference, I would say. LabVIEW will figure out where to assign them. There are specific situations where you know for sure, like you have a perfectly timed loop that has critical code in it, and you know it's going to use up exactly a single CPU's core or whatever. You can assign it to there, and then make sure other code is running in a different area. And so that's always kind of getting the priority on that core. But if you just let it get auto-assigned, it's going to get assigned so that it meets its timing requirements anyways through the scheduler. Any other questions? All right, I'm going to fast forward here. All right, so now we're going to talk a little bit about, oh, you got me there already. She's got me back. All right, so now we're going to talk a little bit more about kind of some advanced tricks you can do with Linux RT that aren't necessarily tools that were available for you on FarLap or VxWorks. So these kind of hit in a bunch of different areas. So the first thing we're going to talk about is another way to look at resource utilization is using proc and the LabVIEW process ID, or if you have your own code running on your cRIO in parallel to the LabVIEW process, you can also look up this information yourself and see how much processes my daemon using or whatever you might have running on your Linux target. Now, this is an example of how to do it in LabVIEW. You can use sysexec to make the call, and then you can parse the results. In the case of this example, we're basically getting the memory usage, allocating a ton of memory, and then getting the memory usage again to just see that it's actually seeing the growth in memory. Some other tools that are available for you to dig even deeper in and see how the real-time operating system is running are tools like ftrace and kernel shark. So ftrace is the tool that is underneath of the real-time trace viewer. So real-time trace viewer will take information from ftrace and bubbles that up in a nice UI for you to see. But if you want to keep digging deeper and actually get in, to like the Linux kernel and see how it's doing process, how it's scheduling things, how different functions are running. You can trace certain events on the kernel, so doing all those types of things. And then in addition to that, there's Kernel Shark, which is a UI that just helps you view the information you get out of ftrace in more of a, kind of real-time trace viewer type view instead of an output on a terminal. Talking a little bit more about Linux, we have the LabVIEW user. So the LabVIEW user is the user that's running anything in the LabVIEW runtime engine. The LabVIEW user has some specific permissions to make sure that we're running at a good level of security. So if you want to run some things, you might not have permission as LabVIEW user to do that. You can install sudo on your target and give LabVIEW user permissions to run certain things, but do that with caution and make sure you understand what you're actually allowing the LabVIEW user to do, what you're giving it access to on your system. Beyond that, you can do sysexec calls. They can't change. They can't call a chirp without approval. So that's kind of actually related to the next point, which is the preempt RT scheduler is actually something that's opt-in on our Linux targets. So if you're going to install any package, it's actually going to go to the completely fair scheduler, and it's not going to schedule that and get in the way of the determinism of the LabVIEW RT code you're running. But if you're writing something, a library or whatever it is, and you want it to run with the RT scheduler, you can actually change that, and you can change the scheduler that is using to run that code. But you can't actually call that from LabVIEW, so it's something that you either need to go in and set, or potentially change your permissions in order to allow calling into your code or running your code in the RT scheduler. Any questions on this? All right, so a couple other things to talk about. So if you're trying to call some external code, you can use the call library function node. This works the same way it does on your VxWorks and FarLab targets. In this case, you're going to compile SO file, and you're going to place that in user, local, and lib, and that's the default location. We'll look for any code that you're calling from a call library function node. And then we also have syslog. So it's a LabVIEW reference library. It's available on our website, and you can go find it. Basically what it does is it allows you to send simple UDP messages across a network or to some type of server where you're collecting that information, and it allows you to send out debugging information about your headless target to a server, so you can say, oh, this is the task I'm working on, or I hit an error, here's some error information, let me send that back. So this is a nice way that you can take a distributed system that maybe have tens or hundreds of serials in it or something along those lines, and channel all of this diagnostic information back to a single source, where then you can look through and see, okay, all my systems are running healthy, or this one had some type of issue but it recovered, something along those lines. All right, so now I'm going to hand it back to Deb, and she's going to talk about switching over to deployment. All
right, so some of you might have experienced this, but running your real-time BI interactively, pressing the run button on your development machine, and then versus writing that and building it into an executable, it might behave a little bit differently. So it's important, if the end goal is to have this running headlessly or at least in the executable form for a long period of time, you also want to test and run this on the deployed settings. So I'm going to share a little bit as to what you can do when building it into an executable to improve performance, and also some things to look out for. Okay, so the first thing when you are building your final application, you want to go into Max and make sure you don't have any superfluous software on there. So if you're going through and installing, this is Compact Rio, for example, like the default software set, it'll probably just give you the minimum, but maybe you didn't know if you needed Modbus or OPC UA to meet your requirements, you just installed support for both to begin with. You would want to go back and remove those just to give you a little bit more space on the target. Some other then settings in Max, separate from installing software, is you can change the Ethernet packet detection on there as well. So BIOS settings for PXI primarily is disabling legacy USB support and hyperthreading. So those are disabled by default, but in case you did turn those on at any point, be sure to go back and turn those off. Just because it introduces extra jitter into the application.
But if you're not using USB, I mean, just having it.
That setting specifically is for like older, I think USB 1.0 settings specifically. So if you're using that, then you need it. But if you're using USB 2.0, then this isn't a setting you need to worry about.
What if you're not using USB at all?
Then this will stay off, and again, don't worry about it. So Yeah, sorry I didn't accurately maybe explain that, but yeah, the disable legacy USB support, again, that's off by default. You only need to turn it on if you're using some very old USB devices, but for anything 2.0, you don't need to worry about that setting. Okay, and then the last one, there's a utility, the NIWeek-based configuration and monitoring. So that's basically the way that you can access Mac's functionality from the browser. It's also called the NINetwork browser, you may have heard. That's something that from that panel you can disable automatically refreshing that console output. So it's a handy thing to do, when debugging, but for your final application you want to turn that off so it doesn't utilize extra resources to publish that. Okay, when you're in the build specification of the LabVIEW application builder, the first thing to do is disable debugging after you've validated your application because that strips out some of the additional plugs we put in place, and also you can remove the front panel that way if you're not using it. That removes the extra overhead and also just optimizes the way that code is compiled. So that's why it's very important to test it. After you've moved away from running it interactively from the desktop, you'd want to be sure to test it after the fact because you might see some changes. Okay, another thing, if you're using the Compact Rio or Compact DAG controller, performance controller that has the embedded UI functionality with the mini display port on the front, you'll want to be sure, if you're not using the embedded UI, that's off. So again, it's off by default. It's a checkbox in Macs to turn that on, and it's a nice feature for your embedded UI. But say if you were playing around with it and you decide not to go with it, make sure that's off, just because it does introduce some baseline jitter if it is driving that display. And CPU usage, excuse me. And then if you are using embedded UI, there's some customizations you can do which are nice for the deployed setting that you can customize for that embedded UI. So one is kind of at the bottom here. You'll see a few of the commands that we've given in the environment. So we put a desktop environment on there, which gives you access to the command line, file browser, configuration settings. That's what we mean here by hiding the XFCE desktop UI elements. So that's something you can run as an initialization using the sysexecvi command at the beginning of your application. Another just nice LabVIEW features that are similar for running an executable on the desktop is setting the front panel to full size and considering removing the title bar, menu file items, etc. And then lastly, there is a kiosk mode that allows you at the executable startup to launch that LabVIEW front panel, maybe for an operator interface where it's always on and always driving. Okay, and then lastly, for deployed systems, we have a recommended tool. Say you have one Compact Rio system that you validated and tested it. Now you need to replicate that exact system, 5, 10, 20, 100 times. We would recommend you take an image of that system using the Replication and Deployment Utility, or RAD. This allows you, from this interface, to scan the targets on the network, grab an image of that, and then turn around and deploy that to multiple targets. There's a lot of questions?
With that, the controllers have to be the same.
Correct. The limitation of RAD is it does have to be the exact same model controller to apply that image. If you have more inflexible requirements where you have different types of controllers, I'd be happy to talk about with you because I'm looking for feedback in that area. But that is something where, say you had a Compact Rio 9068 8 slot and one that's a 4 slot, even for that minute change with different controllers, you'd have to take a different image for both of them.
Looking at these systems, and all is there a way to build this
Yep, the question was, he has a few different personalities or profiles of systems, and he's curious if I can just customize maybe one initialization VI or do some changes between them. There is whitelisting, blacklisting available, so maybe there is a file that, hey, on each system I don't want you to touch any configuration file that's in this location, where the difference between them might just be a configuration file that the operator can change. But otherwise it is really a complete kind of bit-for-bit replication utility.
Yeah. So one thing, RAD is a tool that's just built on top of the system configuration VIs. This tool is actually not only is it available on the website, but the source is available as well, the LabVIEW source. So you could go in there and modify it yourself to make this tool do what you like. So you could actually go in and modify is, okay, if I'm selecting this C-REO and I want to deploy to this specific station, grab this image plus this initialization file and send those down to my controller. You know, if I want specific IP settings or anything along those lines, you can actually customize that yourself. So you can add your own little twist into how you want your system to deploy.
Is this a good way to back up a system too, so that you would deploy it or replace it and have a backup?
Yep.
Absolutely, and you can set a version on this when you are making the image. So the question was, is this a good way to back up the system? And absolutely. Okay, so that was a lot of information to cover. We organized it in thinking about the design stage and thinking long term about your requirements and how you need to modularize them within your application. And I covered the development stage, which covered a lot of tips and tricks, especially some of the new advanced things you can do on Linux, and then quickly wrapped up with the deployment options that you have when finishing out your design after you've tested and validated it. So now a few resources to leave you with, quite a few, but in general I just want to highlight that the Compact Rio Developer's Guide, if you're developing on that platform, a lot of it is contained in that resource. If you want more information on the advanced Linux utilities, go to ni.com/LinuxRT forum. That's our advanced Linux real-time developer forum. And then there's a few other specific links here that these slides will be made available afterwards. And we also link to not the NI specific links here, but just the Linux community links for some of those tools as well. Okay, and then quickly want to make a plug for the distributed control and automation framework session. Say if you're starting a new system development, in the next few months or a year, I'd recommend giving this a look for applications that are, in the low kilohertz range for updating using the Compact Rio scan engine. That's tomorrow afternoon. Okay, so we'll wrap up and we'll be here. Feel free to come up for any questions, but thank you guys.